Good afternoon, we are live now.
Good afternoon, ladies and gentlemen, and welcome to this webinar presented by the FTTH Council Europe. My name is Tom Bambury, and I am Chairman of the Deployment and Operations Committee at the FTTH Council. I will be the moderator for this event. For this event, I will be joined by my colleague, Meersman. Raf, CEO of ComSoft, and is a board member of the FTTH Council also. The topic of the webinar is FTTH and 5G, the success story of convergence continued. And just very briefly to introduce the topic, the Deployment and Operations Committee has been carrying out work on convergence and convergence particularly of 5G and FTTH for a couple of years. We have presented seminars at the FTTH Conference in 2019 and in 2020 on this topic. In 2019, the first study was presented and it focused on the comparing the cost of fibre to the home and fibre to the 5G, and looked at the cost savings that could be achieved through convergence of those two networks. 2020, we took this study a little bit further and looked at the impact of adding in spare capacity at the start when you're building an FTTH network, and how that could create savings for a 5G build in the future that was unknown at the time when the FTTH network was built. So this webinar will present a lot of that work and provide some updates on the conclusions from that as well. Okay, if you move on the slides, please, Raf, one. So we also have, as part of the webinar, the opportunity to use an online polling system. If you can copy the scan code there on your screen, this will bring you to a web page or an app that will allow you to answer some questions. So we'll have a couple of questions throughout the webinar, and this is the first one. So anybody who's scanned the Q code, now you can start answering the questions. And really the question we're asking is, in relation to 5G, looking at the X and Y axis, from your perspective, where are you in relation to 5G in terms of technology, technical details, and in the business case? So on the X axis, the further right you are, the more comfortable you are with technology, and on the Y axis, the higher up you are, the more comfortable you are with the business case. So please continue to answer that, and we will look at how the poll looks later in the presentation. Okay, I think we can see some people are already starting to answer that. So a little bit more of an introduction in terms of the agenda here. I'm just going to do a quick introduction on the topic of convergence and on 5G, just a little background. But that'll be very quick, and then I'll hand over to Raf in a couple of minutes. So that will be the I guess agenda for the day, in terms of the sequence of speakers. If we talk about convergence, moving quickly onto this slide, basically a converged network is a network that can carry out a number of functions, or can support a number of solutions or applications. A lot of the studies we're talking about here is a converged access network that can support FTTH and 5G. And we'll talk more in a minute about the reasons why that's required. You know, effectively what's happening in the world right now is, you know, not just FTTH and 5G, but other phenomena like Internet of Things, like smart cities, and like ever-growing enterprise applications are leading to an ever-increasing demand for optical fibre within the networks to deal with the sheer volume of traffic. So what you ultimately could conceivably end up with is a converged network that supports not just FTTH and 5G, but a converged network for everything, fibre to the everything, effectively. And what we are focusing on in this study is just the combination of the, I guess you call it the retail services, 5G and FTTH. So moving on again, please. Thinking about 5G, I think, unless you've been asleep or on the moon or something for the last 10 years. Everybody knows that the world of mobile communications is moving towards 5G. You know, from 3G 20 years ago, and 4G probably came 10 years ago, and now 5G is the way of the future. And what does 5G deliver that you know, wasn't available in previous generations? I think if you look at this figure here, you're really looking at the three corners of the triangle. On top, you know, enhanced mobile broadband, so gigabits in a second, massive machine type communication supporting things like smart city applications, and then very, very high reliability and very low latency communications. So that would then support new applications such as self-driving vehicles, etc., and other mission critical applications. And what this does, you know, when you think about it, is this enables the future of tech. You know, this creates the vehicle and the platform on which future tech innovations that we probably haven't even thought up of yet become enabled and available to us as consumers. So that's where 5G, it just drives the use for more technology. Moving on again, the other thing that's going to happen is, as this gets deployed, it just creates huge growth in the number and variety of devices that are connected to a network and generating data. The graph on the top left of this screen shows a projection of the number of connected devices worldwide in billions. And it goes from roughly 35 billion here in 2021 and suggests we're getting to 75 billion by 2025. And that's roughly 10 devices for every human being on the planet, which is pretty phenomenal. It's already set 5 devices for every human being on the planet and heading to twice that. As well as the sheer number of devices increasing, the variety of devices is increasing. So things that are not connected today or have not been connected up to recently become connected devices. And you can even see the picture of the agricultural machinery there becoming a connected device. Traffic lights, refrigerators, watches, manufacturing equipment, etc. And then the endpoints at which networks terminate. These are growing and ever increasing as well. Smart cities creating terminations at traffic lights, mobile communications, small cells, manufacturing sites, as well as residential sites and data centers. What this does is it creates a demand for more and more content, more and more data. And in order to deal with that in a wireless network, we have to look at where we go with spectrum, because spectrum is the scarce commodity that is required in order to move information through a wireless network. Legacy mobile networks have used the existing mobile spectrum shown here below 6 gigahertz. 5G uses that spectrum, but will also use very high capacity spectrum in the millimeter wave band. The key thing about this is that it enables very high capacity and very high data rates. However, it is not suitable for very long microwave or wireless links. The range is quite small, struggles to penetrate through buildings and fabrics, etc. So fibre as the backhaul medium is something that is highly desirable when you start to use this spectrum. So these are some of the factors around 5G and 5G as it converges with an FTTH network. The use of very high frequency spectrum, the requirement to converge and use deep fibre, etc., and the ever increasing number of locations and devices that will be connected. So convergence, in order to support that, certainly makes sense from a technical perspective, but what about the business case? And that's really what we're here about today. And that's what the purpose of the studies that the Fibre to Home Council has worked on, is to really look at the business case around this and whether it works from a financial perspective. And with that, I will hand over to Raf. Sorry, one last thing. We will take questions at the end. There is a facility on the webinar for people to submit questions online, and we'd be happy to take questions later on. Over to you, Raf.
Yes, thank you, Tom, for the intro. And yes, it's my great pleasure to give you some more insights on these study results. I would also like to make clear this is a study done under the DNO committee umbrella, so I have the pleasure of being a bit of a project manager on this and therefore also sharing the results, but it is a team effort and we work together with a lot of companies that are part of the DNO committee to come up with these studies. Now, if you look at let's say the key questions within the study that we were looking to find an answer for, and as Tom mentioned, that's like started more than 2 years ago. First of all, when we look at 5G, one thing that we found crucial was to get a real verification of the cell densification factor. How many cells do we really need? That's a very key input to our convergence story. We also really wanted to check and focus on, is there a difference for this business case, for this convergence story in a rural versus an urban area? Then we also wanted to get a feeling about how much fiber you really need to be 5G ready, and ultimately how much cost can we save if we plan a network, a fiber network in a smart way through convergence. So hopefully throughout the presentation we can share answers to a lot of these questions for a number of specific cases, because ultimately what we do is try to come up with answers for some cases. That means it's not necessarily an answer that is viable for any case, but at least they're realistic and aligned with the assumptions. The good thing is today we have a little bit more time than typically in a conference or so. So we will be able also to dive into some more details of the assumptions and the model behind this study result. Now, Tom already touched upon it. 5G, the spectrum usage of 5G is very different from 4G. At the same time, I'm getting often some questions on, yes, but the people are deploying 5G today, but it's for example, in Europe, mainly in this sub-6 gigahertz band. That's true, and we'll come back to that in the assumptions. But let's say it's my firm belief that if we really want to explore all the possibilities of a 5G technology, at some stage we will also start looking at those higher frequencies, because there's simply not enough space in the spectrum to realize all the applications. In our study, we made some assumptions on this spectrum. We looked at a 3.5 gigahertz, and we also looked at introducing 5G on 26 gigahertz to quite popular frequencies. But it's important to notice, if we talk today about deploying a fiber network, and this fiber network would be intended to be used for the long term, well, in 5 or 10 years from now, we may be looking at 6G, 7G. Nobody knows what it exactly will look like, but if there's one thing for sure, that is that it will also use a broad spectrum and will need a lot of that frequencies to deliver more services. So why is that frequency so important? Why do we emphasize on that? Well, that's just laws of physics, looking at the radiation and transmitting wireless signals at a certain frequencies. There is an important impact from a frequency on the coverage, on the reach that you have. And this is nicely illustrated here in this propagation model by Cyrodiil, where you see at a 5 gigahertz frequency from a certain antenna how far the signal can reach. What you also clearly see on the picture is that, especially when it's well positioned through a tunnel, you can reach quite a far distance. But obviously also buildings at 5 gigahertz start to be a real obstacle for a good signal penetration. But if you then look for a similar place but at a higher frequency, the reach is much smaller because the signal attenuates much quicker. And that is the reason why cell densification is coupled to the whole 5G idea, and why you can see, if you want to deliver a service across a certain area, that you will need to increase the number of antennas. And just to illustrate conceptually why this is such an interesting evolution in terms of convergence, look at this concept with a couple of houses on a couple of streets. And if you deploy a fiber network to these homes, and separately you would deploy fiber to the 5G antennas, of course, you can see on the picture there's a lot of double trenching, there's a lot of separate cables being installed. So you would end up with two quite costly networks that you would have to bear that cost separately. Whereas if you would deploy this infrastructure in a smart way one time, or at least on some level of trenching, for example, big ones, it's clear that you can optimize the whole infrastructure, the whole routing, the whole cable and duct amounts to serve these endpoints in an optimized network and reducing the overall cost. So avoiding double trenches where possible, and even avoiding double ducts, for example. So now let's dive into some more details of the model and the assumptions behind some of our key results that we calculated in the study. This is a bit of an overview of this end-to-end model. We applied actually the combination of a wireless 5G propagation model and a wireline calculation model on GIS data. Both models work on detailed GIS data because we really wanted to not just keep it theoretically and use some average numbers, but really take a real area, take the real data, and really show what it actually looks like for those areas. That means we start off with actually a 3D view on a selected area, where we also have candidate 5G poles. We model and select a number of technical parameters on the 5G, and then through this model we can select a logical required number of 5G sites for the future. And with those sites combined with the other demand points in the area, which in our case are the homes, we can do a calculation of a standalone fiber to the home, standalone fiber to 5G, and then a converged single network to come up with those ratios and see what actually can be saved. So we'll dive into more details of those assumptions in a second. First of all, on the areas, I told in the beginning, we wanted also to see what is the situation in urban versus rural. So we ended up with 3 different areas on which we applied our calculations, ranging from a very urban city center with a lot of multi-dwelling units, high-rise buildings, a lot of visitors and public places, all the way to a rural area where we have isolated villages and very scarce population. So we have results on these 3 areas, also the middle one, which is a relatively dense but more single dwelling type residential area. As I said, and this is very crucial, on each of these areas we gathered and were able to achieve this real live 3D LiDAR data, which means we have a 3D virtual environment in which we can actually completely simulate the reality for the 5G propagation and for the fiber layout. As candidate poles, we also loaded all the existing lampposts in the area as a discrete set of candidates to install small cells, where then the softwares can actually select the best subset to reach a certain coverage. Here you see, for example, for the dense area, how this data looks like. You see really the height of the buildings. You see obstacles which are important, especially on higher frequencies. This is crucial to know how your signal will propagate throughout the area. Now, when we then looked at what is a realistic scenario of deploying 5G, what could be the frequencies and the coverage that an operator could want to achieve on this 5G network, we came up with these different cell density scenarios per area. And just to give a little bit more background, you see on the high dense area, for example, we set already one densification scenario that is realistic, is to just deploy 5G at 3.5 gigahertz and try to come to 100% coverage. A lot of the 4G networks are deployed at 2.x gigahertz, so we do operate here at a slightly higher frequency. So there will already be a need for additional cells to get 100% coverage. What we also see in the high dense area with train stations, shopping malls, is that there is a need typically early on for indoor hotspots, because higher frequencies don't penetrate the buildings as good. But then on the other extreme side of a high dense area, what we anticipate there is that we add another layer of, in this case, 95% coverage at a 26 gigahertz. So you kind of get an extremely well covered high frequency, high bandwidth area. That's a quite extreme scenario. That this is not going to happen anywhere, I think, in the next 4 or 5 years, in my personal opinion, or let's say at least not in 2-3 years, I think, in Europe. But it's more or less a natural evolution as well. 5G rollouts will most likely happen in phases where an increased coverage at higher frequencies can be introduced gradually. And that's more or less what we have in these different scenarios here as well. Also important to mention is on the rural area, we looked at already an improved situation versus today to deploy 5G on 3.5 gigahertz for reaching a 70% coverage in the populated villages, which would actually also give a 30% indoor coverage. So it should be clear this is not really an alternative for a pure fixed wired connection, because also the indoor coverage is not as easy. There's no way we look at 26 gigahertz at this time as a business case for rural. So our high dense scenario in rural was based on increasing that coverage, especially also indoor at 3.5 gigahertz to a 92%. So you see the assumptions are quite different in rural and in urban, driven by the commercials of it as well. Of course, there's a lot of different scenarios you can think of, but at least what we see with these assumptions is that this could be a gradual part, a phase rollout in different types of areas that could happen, and that would actually, over time, always increase the number of cell sites to cover these areas. As I mentioned on the 5G side, we also try to put in all the technical parameters and assumptions to see what actually would be the type of service, the type of bandwidth that we could be offering with that certain technology. So you see here, for example, a number of very detailed technical specs on a 3.5 gigahertz 5G rollout. It's not said that, definitely not every operator will use these settings, but they are realistic. They are checked with experts that this could be a way to deploy the 5G network. And what's important, well, first of all, in the bandwidth that we have in a 3.5 gigahertz spectrum, there are some more limitations. So we assumed here an 80 or 40 megahertz bandwidth that is available, so that typically we would have one in an auction. And also important is the signal to interference plus noise ratio is the technical term, but that's basically how much attenuation you allow given the interference and the noise that is added on top of the signals. And that is an important parameter to see how far ultimately we can reach with a certain quality. And you see here as well, with these settings, we assume that when you are in coverage of this cell, that we can offer a 15 to 30 megabits per second bandwidth. of course, as a shared medium. So you see, this is a nice bandwidth, but not a revolution in terms of the bandwidth experience on the device. If you then look, for example, with our introducing 26 gigahertz 5G, you see that there we assume there's a bit more bandwidth available because there's still just some more space there. But at the same time, there is also more troubles to be expected on the attenuation. But you do see as well that our simulations are able to go up to 191 megabits per second delivered from the small cell as a capacity across the sector. So now we start talking about real big speeds in a mobile technology, of course. All of these parameters are configured in the propagation model together with the input data, that is the 3D LiDAR data. And then thanks to our partner Cyrodiil with their model, we were able to identify the best locations for cell sites at these frequencies to reach the required coverage. So let's do another quick question. So you hopefully you still have the page open, or otherwise you can reopen it at polev.com/comsof or scan the QR code. And then you should automatically see this question pop up on how many cell sites that you think there will be in your country, let's say, in 5 years from now, as opposed to today. Is it going to be double, 4 times, 10 times, 30 times? Let's see, answers are coming in, so we should see them coming in live as well. Some mixed results. So a lot of different opinions. Okay. So these are the final results. So we see that the majority thinks between 4 and 10 in 5 years from now. I think that's a pretty good guess, or you know it. But it's also interesting to see it could even go higher. This will definitely depend on the area and the situation in the country. But it seems also everybody is, the large majority is convinced of the cell densification that will happen in the coming years. Now, let's look at our example and what cell densification translates into, which factor we ultimately come up with. So here you see this dense area to illustrate, and you see the red triangles being the macro cells. So this is where currently 4G is being deployed. At first, the first stage, which would be logical, is to deploy the 5G technology on these macro cells at 3.5 gigahertz. It's, I think, a step that a lot of operators will be taking, and when there's announcements of we're rolling out 5G, I think today it's a lot about this first step. But as we mentioned, well, at 3.5 gigahertz, if you do the analysis from the existing macro cells, you will find that there are islands with not good enough coverage. So to reach 100% coverage at 3.5 gigahertz, we can see that there is a need already for introducing some small cells in between in the black spots or the white spots, however you want to call them, from the macro sites. In our calculation here, we introduce 11 additional small cells in this area to reach 100% coverage. And as I mentioned, we also saw in this region that there are 13 interesting indoor hotspots, like a train station, like a museum, like a shopping mall, because there are a lot of visitors, there's a lot of users, and there is some issue with the indoor coverage in those areas. So that's you see we are going here from 6 to 30 already in order to reach this type of coverage. If we then say, okay, let's put another layer on top of 26 gigahertz coverage for 50% of the area, it means if you have a mobile device and you would actually be in the area, you would have a 1 on 2 chance that you have the 26 gigahertz high bandwidth. If you are not in reach, your device would fall back to a lower speed, of course. Now, to reach 50% coverage, we calculated that we needed a minimum of 29 additional small cells, the ones here in blue, because we're also reusing the small cells that we already had for 3.5 gigahertz to deploy the 26 gigahertz. So in total, we go now to 60 cells, or a factor 10. And then ultimately, ultimately we say, let's try to reach 95%. Well, you already see for 95% coverage, we need to introduce a lot of small cells. Actually, it's a total of 87 additional small cells on top of the earlier ones, reaching about a factor 20. So if you, of course, if you are convinced a 95% coverage at 26 gigahertz is not realistic or feasible anytime soon, then of course this factor 20 is overestimated. But again, when we talk about preparing our networks and infrastructure for the future of the mobile networks, we also need to consider the lifetime of the fiber infrastructure that is quite long. So we do need to anticipate this unknown high density future. Now, through all these calculations, we found ideal locations for the 5G mobile sites. So that's the points that we then want to fiberize. So we feed these points into the map, and we also add the homes because we also want to bring fiber to the home, to the whole area. We will specify the architecture of a fiber network, which means this can be a hybrid point-to-point network, and we'll come into some more details later on. So we feed all of that input into the calculation model, and then we calculate on the map an accurate, realistic FTTX network design with an automatically generated bill of material that provides us with the cost details to build this network. So as such, for any densification scenario, for any area density, and for any of the technical assumptions, we can calculate all the necessary costs to see what comes out. Now, on the FTTX parameters that are configured, some more details here. So there's a lot of variations depending on the country, the operator, the area, how networks are being deployed. So we just took some standards. Of course, you can rerun the model with a lot of variations, but let's say we've taken some assumptions here within the DNO committee that were supported in several projects across Europe. That means for fiber to the home, we are actually calculating a model with a 1:32 splitter in the distribution point, so a GPON network. We foresee 2 fibers per home. We have some cabinets where we have flexibility, up to 96 homes on a cabinet. The network initially is considered to be deployed completely underground using microducts and air-blown fiber, and we deploy some mid-span access feeder cables of 96 or 48 fibers. For the fiber to 5G, we calculated with some variations, different fiber counts, whether we would foresee 12 or 4 fibers per cell site. But we also played around with, do we make those fibers point-to-point, or do we make them point-to-multipoint? Ultimately, most of our results are based on this third scenario, where we would actually bring 12 active and 12 spare fibers to every cell site. This means it's also foreseen typically for multiple operators to put their wireless technology on the site. But we do introduce some level of fiber aggregation through a splitter higher up in the network in order to reduce that fiber count throughout the network. On the costs, also very important, there is a difference between the urban and rural areas, and the numbers we've taken for the major results are like 80 euro up to or down to 35 euro per meter for trenching. These numbers are actually also aligned with the former FTTH cost model for Europe, which we did eight years ago or something. So they were also gathered by several members of the DNO committee. The costs are obviously important. There are also geographical differences. So in some countries, for sure, trenching costs will be much cheaper than this. In some countries, for an urban area, it could be more expensive. If you would use micro trenching, the cost would be again completely different. Again, these are things that we could change in the model, but now we work with, let's say, this as a starting point. And then ultimately also important to mention that the costs we are reporting focus on that outside plant passive network. So we don't include things like ONT, OLT costs or fiber, 5G active equipment, or for example, spectrum costs. All of those costs are not envisaged. We focus on how much of that shared fiber infrastructure outside can actually be saved in the convergence. Here you see a map to show you the real results that were generated, that it's not an Excel model, but it's really a detailed model. And if you think about all those streets and houses and you look at the locations of the 5G antennas, I think it's fairly easy to see the opportunity that lies ahead, especially if you look at this high density. You're virtually in every street or every one another street, you are deploying fiber for the 5G case already. But you're also coming into that street for the fiber to the home network. So zooming in, you clearly see that building this once will drastically reduce the overall cost because you can avoid a lot of double trenching. Okay, let's go through some of the main results of this study and model based on the assumptions that I just presented. We already saw these densification factors that we assumed, factor 5 to 20 in urban. And again, it's important to see that these are typically probably rather rollout phases and stages rather than just a future end result or end scenario. On rural, we have, for example, here also what you could see as a phased rollout, but we see there that we go from 2 macro sites today to a situation where we had 16 sites to reach a decent 3.5 gigahertz coverage also indoor. So you see that the factor here is a bit smaller than in the urban area with these assumptions. Here you see that illustrated as well for a village, where it's also, well, crucial to see the difference in the indoor coverage. This is where the extra cells are needed. So that gives us ultimately also the cost results. We calculated the cost for a standalone fiber to the home, standalone fiber to 5G, and then a converged network, which the X%, the blue arrow, would be the percentage that we can save. Now, if we relate the amount here that we can decrease versus the standalone of fiber to 5G, that is what we were looking for. How much of the 5G standalone fiber network can we eliminate by building it in a converged way? Now, as a last small polling question there, again on the same page, you can provide your answer to this question. What percentage of cost of the 5G standalone do you think can be saved typically in our calculations here with these assumptions through convergence? Is it 10, 20, 40, 60, or 80%? If all goes well, we see the answers coming in. So we see there is a slight preference or idea about the 20 to 40% savings. So 20 to 40% of the fiber to 5G cost that can be saved through the convergence. Well, let's have a look at the real results that came out of our calculations. So this is the example high dense area, so very dense city center with the ultimate high dense cell scenario. And you see we ended up with a network of 8.5 million euro for the fiber to the home standalone, 1.85 for fiber to 5G, and about 9 million for the converged network. That means in this case, we could actually eliminate 75%, 74% of the standalone 5G fiber network by building it in one case. So even higher than what is expected as we see in the polling. And the actual additional cost is only 500,000 on top of the 8.5 million, represents only 5 to 6% of the original investment for a standalone fiber to the home network. Now, as we mentioned, we applied these calculations to all our scenarios, so also to low dense areas and low cell density. So you see the 74 and 5.6 that I just showed you on the high dense area, high cell density. Now, interesting is that if you go to low cell density, less cells means a smaller fiber network, means it's even easier to bring let's say, build it into the fiber to the home. So it's almost for free that you can accommodate that. But I think more importantly, it's also interesting to see that on the rural areas, we also have still 65% savings, which is, I think, more than we anticipated before. So it's not that different, the savings that could be achieved through this convergence. So the convergence definitely is not just a thing in the urban areas. It also has the benefits in the more rural areas. One other calculation that we did was to switch over from an underground to an aerial network. So introducing poles and deploying aerial cables obviously will bring a whole other flexibility to the network. And that does translate into quite a different number. What you see for this scenario underground, where we had 83% saving through convergence. In an aerial case, the network initially is cheaper, but the extension and the level of convergence opportunity is a lot smaller. Of course, because it's less trenching, less ducting, and more cable costs, which are less easy to share. So again, assumptions are crucial. If you have a hybrid underground aerial model, it may end up somewhere in between, but of course, the best thing to know is always to calculate it with the real numbers. Now, just on those results, a lot of questions that came was also, okay, that's fine if you know what the future of the 5G looks like, if you know where the antennas are gonna be installed, but we don't know it typically today. So how can we be 5G ready without knowing where 5G will really be? Well, that means you need to foresee spare capacity in a fiber rollout today for an unknown future. And the question is, how much spare capacity would be enough given that uncertainty? So we built further on these models and on these data. We took the high dense area again, same area. We introduced 12, 24, and 48% spare in 3 scenarios. And then we said, okay, let's then assume we built that network with that spare that is reserved for 5G. And let's assume in 5 years from now, we know at that time what the 5G looks like. We consider it to be the high cell density scenario. with 95% coverage on 26 gigahertz. And let's see how much of that future network fits into our spare capacity. So it's a bit similar, but with a level of uncertainty at the time we built the fiber network. Again, we're using microducts in the assumptions. We're building it based on a certain number of ducts or subducts that we actually reserve for 5G, averaging out to these 12, 24, and 48%. And then illustrating it here, you see that we would actually deploy these microduct bundles for fiber to the home, but reserving always a minimum spare ducts, the blue ones there, that should not be used for anything else than the future 5G network. And then we see, depending on how much spare there is, that the 5G might fit into it for some parts, and then we avoid double trenching. But for some parts, the capacity is full. And there may still be additional trenching because we didn't anticipate enough capacity. Looking at the costs, you can see here a standalone at 8.5 million euro as before, the standalone 5G at 1.8 million, but we also discount that over 5 years. So the net present value with 8% would be 1.25. So we have a total net present value of building two separate non-converged networks. And then if we introduce 12% spare, we see a very slightly increase of the cost, not a lot, because we already have ducts that we can reserve for this. And we see a decrease of the 5G. So reusing that spare capacity is good, but still overall, the decrease is not significant. Going to 24%, we see the increase a bit further, but especially there we see a big decrease of the 5G cost. Going to 48%, that increase a bit higher, but the decrease is not spectacular anymore. And to reference the previous result of building it today, knowing what 5G would look like, would actually end up with almost 9 million euro. Bringing that together, the conclusion here in this case, stacking those different values, you clearly see that, well, 12% in these cases with these assumptions was clearly not enough. We didn't get the full value of the convergence out of this network. But in these assumptions, with the 24%, we were able to capture the majority of that value of convergence. Or put a bit differently, here you see the how this cost for 5G can be reduced by reusing the different levels of spare capacity. Now, I do have to warn a bit with this result that what we clearly do not want to state is that every case 24% will be the ideal or best spare capacity for 5G. Again, it depends on the assumptions, the case, the density and the parameters that you would put in. But nevertheless, again, a very realistic result based on realistic input from start to finish. And interesting to see that you do need to foresee the right level of spare capacity because 5G is quite heavy on fiber demand in the future. Yeah, 12% is already significant, but clearly not enough under these assumptions. Okay, so our key findings of the whole study was that there was a huge cost saving for building the fiber to the home and the 5G network together. This was the first result. Between 65 and 96% of the 5G fiber cost could be eliminated by building it together, at least for the underground scenario. Then we also looked at if you would build it today, fiber to the home, with only limited spare capacity, 12% or lower, well, you would incur additional costs for the future 5G network over a reasonable lifetime of the fiber. It's not like the fiber network is going to be renewed in that time frame. So we ended up with 2 to 3.5 times as expensive to roll out fiber for 5G. This is also one of the reasons why we definitely believe that areas where there is spare capacity in fiber rollouts today will be the areas where 5G networks could be leading in the future, because of course this will impact the business case enormously if that fiber spare capacity is available or not. And then lastly, as a, let's say, a tip, good practice is, okay, often you don't know yet what that future 5G really densified scenario will look like, but there is a way to anticipate on it, and that's by building sufficient spare capacity into the networks of today. So that's, let's say, a walk through our complete 5G convergence model and study. I would definitely like to thank our contributing members and people from the working group on this study, who contributed a lot with the discussions on assumptions, model, and calculations and results. And I'm happy to hand over to Tom to treat any questions that we may have.
Thank you, Raf. And we'll let you catch your breath there for a second, because that was a whistle-stop tour of a couple of very large studies. And I think some of these slides are available already on the FTTH Council website from previous seminars and the FTTH conferences. And there's also a white paper that we've published on this topic also that can be downloaded from the FTTH Council website. So if anybody has interest in exploring the topic further, I would certainly encourage them to go and look at those initially.
Maybe good to mention, Tom, just quickly, is that it's indeed, this presentation combines a lot of slides from previous workshops and study presentation. So I do think indeed the good thing is this is a bit of a total overview of everything we did over the past 3 years. So definitely the best version if you're interested. A lot of the other presentations on the website will typically only highlight a part of this. So this is, I think, a nice overall overview of everything.
Yep. Although I think there's very few people who could go through it all as quickly as you have in the last 35 minutes and take it all in. I have just a couple of questions, Raf. I guess one on the first study regarding the savings of building a converged network versus building standalone networks. If you look at say either the high cell density or the medium cell density scenario, and you consider going from a densely populated area to a suburban area to a medium area or to a low populated area, you can see that the savings seem to increase and then they decrease again. Is there any reason why that occurs, or is it maybe within just the boundaries of error of the simulations?
Yes, I think so. It's a very good observation. I don't have a complete logical explanation for it, except that indeed what we really do is take 3 areas, 3 different cases, and we calculate it, and these are the numbers. And results in this kind of simulations is not always completely covered by the assumptions you're looking at. There's indeed sometimes other assumptions underneath that could influence. For example, one influencing factor could be the difference in the unit cost of trenching between a suburban and an urban area. But we have not been able to really pinpoint or find it out. So I think the conclusion of this is that every case is different. And it's what we want to avoid a bit is that these numbers would be used also as the truth and the barriers and the extrapolate on this where you are. No, actually every area can have different aspects. We illustrated the 3 real areas, but it's not 100% guaranteed that the same number will apply to every medium dense area, for example.
That's fair. Okay. And then relating to the second study, which I think probably is of great interest to people who are considering right now building FTTH networks and trying to understand what their spare capacity policy should be, because that truly has to be one of the big questions: is what's going to be the need in the future? How many fibres do I really need? How many ducts do I really need, etc. And this has put some interesting numbers on the table there. Just one thought that struck, one question we received regarding this was the sparing policy here seems to be around spare duct. And if you had taken an approach of, instead of maybe using 96 fibre cables, to go with a 288 fibre cable or a 432 fibre cable, would that deliver similar savings, or would it greatly increase the day one cost of the FTTH network so much that it doesn't make sense? So that's the comparison between duct sparing versus fiber sparing as your day one sparing policy.
Yeah, it's a very good question. You could actually perfectly also do it on a fiber level to foresee spare fibers for future 5G. In fact, well, I briefly touched upon that aerial case where on aerial, yeah, you would probably have to do it that way to foresee immediately the fibers if you really want to benefit from the convergence. But the reason why we did take the duct level is that you do have a lot of flexibility indeed. Building the duct network on day one is not the most expensive. And indeed, in the end, 5 years later in this scenario, when we then know where 5G comes, obviously we only blow the necessary fiber capacity through the empty ducts where they're needed, which also indeed means we're not putting a lot of cables in the ground where they're not needed. So it is indeed a bit of a balance between the pre-investment and then keeping a flexibility to actually deploy additional capacity where ultimately you need it in 5 years from now that you may not know today. So it's indeed a scenario. Well, we could calculate it on a fiber level as well, but it would indeed incur the additional cost. And then, yeah, I'm not sure overall if that will be a more cost-efficient way for the underground scenario, at least.
Okay, thank you. We have a question come in on the webinar as well. To what extent do you consider 5G millimeter wave as a complement or a substitute to FTTH? I guess that's as much a question for the council as it is for the people presenting this webinar. I would say that the council's position on that would be that the technologies are complementary, and that there will always be a need for the fixed network termination point to deliver stuff that we don't even know about yet. So it's definitely a complementary technology, and from my perspective, and I'd be happy for you to maybe chip in there as well if you have anything else to say on that.
I obviously fully agree in the sense also that if you looked at some of the numbers I shared, if you want to really deliver high bandwidth to all residential users, you have two problems, I think, with 5G only for that, and assuming you wouldn't need a fiber to the home. The two things is, one, you would need to go into the high frequencies because we're talking about bandwidth needs that are very high, especially for home users. More and more that bandwidth need is high. So you're talking about moving very closely with your antenna. So fixed wireless access examples on 60 gigahertz, for example, in the US have been deployed. But then you also have that issue of the higher the frequency, the more the line of sight and the even like penetration in the building is becoming a problem. I've even heard, for example, an anecdote of an 60 gigahertz fixed wireless access solution that was working very good in the summer. No, sorry, in the winter, having a line of sight to a building antenna, and then suddenly in spring, leaves came on the tree, and the signal degraded suddenly. So. I don't think it's the thing for high bandwidth that would replace the quality and the stability, let alone on sustainability, where I think DNO is also doing some study work on the fact that fiber can actually be also a low energy sustainable.
Indeed. Yep, this is true. Okay. We received one other question which came in by email prior to the webinar regarding optimizing the microducts and microcables and bundles of duct, and I think we've addressed that in the content of the webinar. If the individual or the company that sent in that question would like to clarify further on the question, please feel free to send in another email, and we'll attempt to answer it. But I think, Raf, you covered it pretty well in terms of the sparing policy on the ducts, etc. So I don't need to discuss that any further. I don't think there are any further questions. I don't see any on the webinar. So with that, I think we can draw the session to a close. Thank you very much, Raf. Thank you very much to the Council for organising the webinar, and indeed to everybody in the audience, thank you for your time and your attention.
Yes, thank you. Have a good day.
Thank you.